This is the solution video for section 7.1, problem number 16. All right, so the problem says find the exact area under the graph of y equals x squared plus 1 from x equals 1 to x equals 4 by dividing 1 to 4 into n equal subintervals using circumscribed rectangles. All right, so this is the process that we laid out in the video for slides 8 and 9. All right, so what we want to do is we first of all want to recognize this graphical situation, right? So x squared plus 1, parabola, shifted up, y-intercept of 1, all right? And we're going from 1 to 4, all right? So we are trying to find this area underneath this curve from 1 to 4. All right, so what does that mean? Well, that means our function, f of x, is x squared plus 1. Our interval is 1 to 4, so that means that a is 1 and b is 4. All right, and we're using n rectangles. So remember, if we're trying to find the exact area, that means we're going to end up using an infinite number of rectangles. All right, so how does this work? Well, the exact area is going to be found by taking the limit as n approaches infinity of the sum from k equals 1 to n of, and you recall, we talked about this earlier, delta x times f of a plus k delta x, right? So remember, delta x is the width of the interval. So b minus a, so 4 minus 1 is 3, divided by n, the number of rectangles. All right. And so we're going to insert that information and remember that f is x squared plus 1. So we're going to evaluate the limit as n approaches infinity of the sum from k equals 1 to n of delta x, which is 3 over n, times the function, which is x squared plus 1. So we're going to take x, which is a, in this case, 1, plus k delta x, which is 3 over n, quantity squared, right? That's x squared plus 1. And so it's very important to remember that the 3 over n is distributed through everything here, including the plus 1 at the end. All right, so now this is what we want to evaluate. So limit as n approaches infinity of the sum from k equals 1 to n of. All right, so first thing I'm going to do is I'm going to expand the 1 plus k times 3 over n. All right, I'm actually going to write that as 3k over. All right, so I have the 3 over n here. All right, if I expand that, I get 1 times 1 is 1, of course. And then I have plus. Now, this would have been 3k over n times 1 plus another 3k over n. So 6k over n's plus then that thing by itself. So that'd be 9 times k squared over n squared. Right? Then I also have that plus 1. So actually that's just going to end up being a plus 2, right? Because those two can be added together. So now I'm going to evaluate the limit as n approaches infinity of the sum from k equals 1 to n of. All right, now I'm going to distribute the 3 over n. So 3 over n times the 2 is going to be 3 times 2, so 6 over n, plus, now I distribute here, I get 3 times 6, 18, k over n squared, plus 3 times 9, 27, k squared over n cubed. All right, so now I am going to split this up into 3 separate summations. All right, so now I have the limit as n approaches infinity. That's an n, not an h. N approaches infinity of. All right, so now I have the sum from k equals 1 to n of 6 over n plus the sum from k equals 1 to n of 18k over n squared. Then I have plus the sum from k equals 1 to n of 27k squared over n cubed. All right, so now I'm going to use my some more properties of summations. All right, so first one, the sum from k equals 1 to n of 6 over n. Remember, n is a constant, unspecified constant in terms of the summation. And so the sum of a constant from 1 to n is that constant times n. So in other words, 6 over n times n. And don't forget, we have not evaluated the limit as n approaches infinity yet. All right, plus, all right, now, here, I'm going to bring the 18 over n squared out, like we talked about in our properties of summation. So then I have the sum from k equals 1 to n of just k. What is the sum from k equals 1 to n of just k? It is n times n plus 1 over 2. All right, then plus the last summation. Remember, just like earlier, I can take the 27 over n cubed out, and then I'm left with a sum from k equals 1 to n of k squared, which you might remember is n times n plus 1 times 2n plus 1, all divided by 6. All right, so now I dealt with the summations, and so now I want to evaluate the limit as n approaches infinity of each thing. All right, first of all, 6 over n times n, that's just 6. So the limit as n approaches infinity has nothing to do with 6, plus, now I have the limit as n approaches infinity of 18 times n plus 1 over n squared times 2. So it's actually going to end up being 18n squared plus 18n over 2n squared. So remember, the limit as n approaches infinity would just be the leading coefficient of the numerator divided by the leading coefficient of the denominator. In other words, 18 over 2, or 9. So I have 6 plus 9 plus. All right, this one, just like earlier, I'm going to multiply this through. So 27 times n times 2n, that's going to be 54n cubed plus, well, some other stuff I don't really care about because the denominator is also going to have an n cubed. And so remember, I'm evaluating the limit as n approaches infinity. Don't forget about that. And so if we do that, it would just be found by taking 54 over 6, which you could divide by 2, which is 27 thirds, right, which is just 9, right? So 6 plus 9 plus 9, so I get 24. So the exact area under the curve is 24.